Okay, you should have your notes out of the two videos dealing with nuclear change or nuclear decay. We're going to take some notes here. You're probably going to want to copy down certain equations that are dealing with the different types of decay. So, basically, when we look at some ICANs for nuclear decay, I can understand radio decay results in the emission of an alpha particle, a beta particle, or a gamma ray. I can identify the process that is occurring in the nuclear reactions that are written in a symbolic form. And what that just means is written with the chemical symbols, atomic masses, atomic numbers. Okay? I can identify whether it's alpha decay, whether it's beta decay, electron capture, or positron emission. So I can distinguish between those four types of nuclear reactions. So basically, given an equation, you can pick it out and say, yes, Mr. Braun, that is beta decay. Most isotopes that are occurring naturally are stable. A few are unstable. And we talked about the nuclear stability and said it's comparing the number of neutrons and the number of protons. So that number, neutrons to protons, gives us whether they are stable or not. Unstable isotopes become stable by releasing different types of particles. That's where we're going to see the alpha particle, the gamma rays, the beta particles. So by releasing different particles, they become stable, they being the unstable isotopes. That process is what we call radioactive decay. And the elements that are doing that are what we call radioisotopes. I also put radionuclides there, or excuse me, nuclides. But most of the time, when I see this, I see it in the form of radioisotopes being the names for those. Now, when we're talking about radioactive decay, I just told you we could have an alpha particle, a beta particle, or a gamma ray that is released, that is emitted. So, when we talk about alpha decay, it is where an alpha particle is being released, and that alpha particle is identical to that of a helium nucleus. Well, what does that mean? Well, we know helium has how many protons? Go ahead and take out your periodic tables, because we're going to be referring to those a lot today. Helium has how many protons? Malcolm? Protons. 2 protons, excellent. Helium has 2 protons. Now, the most common isotope of helium is going to be probably the closest to its atomic mass that it's rounded on our periodic table. So that's going to be a 4. So when we're talking about a helium nucleus, I can see up here that I have 2 protons and I have 2 neutrons. So my atomic mass is going to be 4. My atomic number is going to be 2. So it'll be a helium 4 over 2. Okay? So when I have alpha decay, right here is the equation that I'm going to need to memorize. So I'm going to give you a second here and write this down in your notes, because we're going to use this tomorrow also. We're just going to touch the surface today. We're going to do more of this tomorrow. How do I recognize this as alpha decay? Right there. See the helium 4-2? That helium 4-2 right here is the alpha particle that we're talking about. So when I see that helium in the product side, okay, when I see that helium in the product side, I can see that there's alpha decay. Now, what is this actually telling me? Well, X right here is my unstable radioisotope. It has a mass, it has an atomic number. In order for that to get Y, which is a more stable isotope, okay, or a more stable element, it has to take 4 and 2 off. Why 4 and 2? Because it's releasing a helium, which is 4 and 2. So, if I come up here and I say, all right, here's my unstable atom. Here's a more stable atom, and here's my alpha particle. Now, I think we can do some good math, can't we? Some addition and subtraction. I don't think we're too bad at that. So let's look at this. Here I have, I think that's radium. Let me double check. Yep, here I have radium. Radium has 88 protons, and its atomic mass is 226. Now, this radium is not stable. It's an unstable isotope. In order for it to become stable, okay, it is going to split. And one of the things that's released right here is this helium. The other one is radon. Now, how do I know that it's radon? Well, what happens if I subtract 4 from 226? Well, that gives me 222. What if I take 2 off of 88? That gives me 86. What is element number 86 on your periodic table? How about radon, right? So we've taken these two numbers right here, and we've subtracted the 4 and subtracted the 2. So when we have the alpha decay, this radon here, this guy over here, is a more stable compound. Why is it more stable? Remember, the neutrons to the protons, and radon's a kind of bigger one, right? So we would expect it to be more in the 1.5 range. Yeah. It's not. This is just the alpha decay. Okay? Beta decay will be different. Okay? Alpha, that's how we recognize alpha decay. There's always going to be a helium released. Okay? So, if I look at this, here's my equation once again that I told you to write down in your notes. Okay? Right here is what I just showed you. So if I'm writing an alpha decay reaction, I'm going to write it like this, where you can see that the 88 minus 2 gives me 86. All right? So this right here will give me what element Y is if I just follow this, A minus 4, Z minus 2.
Will there ever
I'm not saying that it couldn't happen, but the whole idea of the decay is to create stability. Okay, we're going to talk about some things here where it's called a chain reaction later on, but let's wait for that. Okay. Now, let's look at this right here. We got this radon right here. So I guess this will answer your question a little bit there, Malcolm. Okay? Because we're now breaking down the one we just had to make it more stable. All right? So if I am going to do my alpha decay here, okay, my A over Z here, and I really wish, and I might even change this to put that A minus 4 and the Z minus 2 in there. Because what's this element going to be? Okay, what's this element going to be? What matters on determining the element? Which one, the A or the Z? The Z, right? Because that's our protons. So what is Z minus 2 going to give us? What number? 84, okay? And what is 84? Polonium. So what's my top number going to be? What's my A going to be? 218. Pretty tough math, right? 218, 84, polonium. How do I know it's alpha decay? Because what? Because I have a helium right here that is being emitted. So I know that is alpha decay. Here's another one. Go on the other way. Now I have the more stable element. How am I going to get X here? How am I going to do that? Yeah. Add 2 to the Z. If I add 2 to the Z, it gives me what number? 92. And what's element number 92? Yeah. Uranium. Okay? So what's my A for uranium going to be? What's my 234? Good. So 234, 92. So I can go to the unstable to stable or vice versa, the stable to unstable. I could do it either way, and this is just setting up my equation based on what I'm given. Now, beta decay is different. So, beta particle is a fast-moving electron, which is emitted from the nucleus of an atom that's undergoing radioactive decay. So the beta particle is a fast-moving electron. So here's how I'm symboling this little blue guy right here. That is that fast-moving electron. So when beta decay occurs, a neutron is changed into a proton and an electron. So by that fast-moving electron being emitted, we're changing a neutron into a proton. Well, let's stop and think about that when we're talking about Z and A. Okay? When we're talking about Z and A. Z is the number of protons, right? If I have a neutron changed into a proton, that Z is going to be going up 1. So does it change the element? Absolutely. Absolutely. So when I'm doing beta decay, the nucleus has 1 less neutron, but has 1 extra proton. Does that change my top number? Changing a neutron to a proton. Think about this. Okay, what is the top number? Neutrons plus protons, right? So if I change one of those, does it change that top number? Uh-uh. The only one that's being changed is the bottom number. Okay? So the number Z increases by 1, but A stays the same. So in my equation here, if I have this polonium right here that is undergoing beta decay, I'm changing a neutron to a proton. So my new Z is going to be 85. My new A is not going to be a new A. It's going to be the same. It's going to be 218. So when I break this up, okay, I have 218. I have 85. Element number 85 is astenine. And here's how I symbolize that beta particle. Okay, that is a Greek B with the -1 and the 0. Now, I've also seen this written as, instead of a beta particle, what did we just tell you that that was? A fast-moving electron. So I've also seen this written as an E. So 0, -1, E, symbolizing the electron. So don't be confused if you see the B. Don't be confused if you see the E. Different textbooks, different websites will have different labels for that. Okay? If I remember right, and I would have to look this up, but if I remember right, I think WebAssigns uses an E, not the beta. Okay? It uses an E as in the electron. So, when I talk about my equation that I need to remember for beta decay, here is the one that you need to write down in your notes. So, once again, the one I just showed you with the polonium, 21884. Well, if I take Z plus 1, I get 85. That gives me astenine. My A stays the same because all I'm doing is changing a neutron to a proton and getting rid of this high energy electron, this fast moving electron. So, can I figure out what Y is going to be here? I can see that I have beta decay because here's my electron being given off. So, what am I going to do to Z? I'm going to add 1 to it. So, what's Z plus 1? It's going to give me 91. Element 91 is proactium. What's my A going to be? The same. Okay? So, 234, 91, proactium. And there's my beta particle. Can I go the other way? Okay, can I think of this the other way? Well, here's lead, 21082. So lead is my stable right here, my stable element. So in order to get my unstable one, what am I going to do to this Z right here? I'm going to subtract 1. Pretty tough math. 82 minus 1 is 81. What's element number 81? Thallium. What's my top number? What's my A going to be? 210. So I have thallium 210, 81 as my unstable one. It decays. It undergoes beta decay to form a more stable lead element. And there's my beta particle that is being released. Electron capture, okay, is the third type of nuclear decay we're going to talk about. An electron capture is the opposite of beta decay, of a beta emission. Remember, beta decay, that fast-moving electron was given off. What do you think about electron capture? What's going to happen? The electron is going to be captured by the unstable nucleus. Okay? So when that happens, when the electron is captured, the proton turns into a neutron. So once again, is my top number going to change? No, because a proton turns into a neutron. Is my bottom number going to change? Yes, it is. Okay? Yes, it is. How's it going to change? Well, thank you. How's it going to change? That Z right there, okay, we're going to capture that electron, so that proton's going to be changed in a neutron, so my Z is going to decrease by 1. So when I am writing my electron capture, I write it as so. So go ahead and copy this into your notes. So what I want you to do is I want you to notice, okay? I want you to look at alpha decay, check. I want you to look at beta decay and electron capture. And I want you to notice where that electron is in terms of the yield sign, the arrow. Notice where the electron is. In beta decay, what side of the arrow is the electron on? The right side, meaning it is given off. Okay? In electron capture, which side of the arrow is the electron on? The left side, meaning it is taken in. Okay? So that's what I'm looking for to distinguish between a beta decay and an electron capture. So if I have electron capture, here's adenine 21885, okay? I'm going to capture that electron. By doing so, I'm changing a proton to a neutron. So my protons are going to decrease by 1. 85 minus 1 is 84, which gives me polonium, element number 84. So polonium 21884. My Z changes, my A stays the same. So, as I am capturing this particle, the atomic number decreases by 1, the mass number stays the same. So, it says, what is Y? Here's another equation. What is Y? All it's asking me for is, what's element Y on this electron capture? Well, what's 18 minus 1? 17. What's element number 17? Chlorine. What isotope of chlorine is this going to be? 37. Chlorine 37, 17. Write the equation for the electron capture of nickel 59. Okay? So I'm dealing with nickel 59. What does nickel 59 tell me? The mass is 59. Obviously, my symbol is nickel, Ni. What is my atomic number for nickel? 28. So I'm going to have nickel 59, 28. When I do the electron capture, the 59 is going to lose 1, or excuse me, The 28 is going to lose 1, so it's going to be 28 minus 1 is 27. Element number 27 is cobalt. So this will be cobalt 59. Find the missing starting material. Here we go. I've got some carbon 14 right there. Okay? Carbon 14 right there. What's going to be my starting material? Well, what do? My 6 is going to do what? Gain 1 to make it 7. What's element number 7? Nitrogen. So this is going to be 14,7 nitrogen. So this stuff, ladies and gentlemen, is not difficult math. The difficult part is distinguishing what I got going on and memorizing my equations. The last one we're going to talk about today is positron emission. Positron emission. A positron is like an electron, but it has a positive charge. So instead of signifying this as that blue fast-moving electron, this is going to be a green one, which is going to be a positron. Okay? During positron emission, a proton changes into a neutron. Once again, a proton changes to a neutron, so does my A change. It does not. If a proton changes into a neutron, does my Z change? It does. How does my Z change? It decreases by 1. So, if I'm looking at this equation, which go ahead and copy this down into your notes. This is our fourth and final one today, positron emission. So as I'm looking here, okay, how do I identify positron emission? Well, I see that the plus electron, the positron right there, is being released. So, that mass stays the same, we know. There's my positron. So when I do positron emission, here's that adenine again. What's going to happen? Well, I'm going to have the positron, and I'm going to have a proton being changed into a neutron. So my 218 stays the same. I go from 85, I lose a proton to go to 84, which is polonium. So basically, the proton splits, emitting the positive particle, leaving a neutron. The atomic number decreases, the atomic mass stays the same. There's my equation you should already have in your notes. So, in this equation, what is Y? Can you tell me what Y is? What is it? What are we doing to Z? We are decreasing by 1, right? So what is 5 minus 1? 4, which is beryllium. So we're going to have beryllium 8, 4. And my positron. Now, I'm going to give you a second here. We'll see how you know this, how good you know this. Write the equation for the positron emission of oxygen 16. So write this equation in your notes, then I'll show you it. Now, what do you think? Oxygen 16 right there. What's the bottom number going to be for oxygen? 8, correct? So what's 8 minus 1? 7. My mass stays the same because the top number does not change, and then I have the positron being released. What is the starting material here? Okay, can we work this backwards? I have copper, 2966. All right, so if I'm working this backwards, I have one more proton, correct? So what is element number 30? Zinc. So what's my top number for zinc going to be? 66. Okay? 6630 zinc. So this would be zinc 66 if I were talking about which isotope of zinc.